What time is it?
It's time for a juice party.
Isn't it time for a study guide party?
No.
How about a study guide party?
No.
How about a study guide party?
No.
How about now?
Oh, okay. Let's party. Party. Let's party. Let's party. Let's party.
Whoops. Bye, it's you. Ah, hey, I bet you thought that was me at first. Surprise! All right, so we are here for the study guide party, and we're going to start here on page 93 in your notebooks. So you should have most of this done, and if not, then now's your chance. Okay, so we are going to look over here at this picture, and let's get my pen here. So this is a convergent plate boundary, and how do you know it is convergent? So, first of all, do you see those arrows? That's a pretty good indication, because if you put your fingers like the arrows, go ahead, do it. Come on. Okay, so you put your finger like the arrows. You can see that they're coming together. Convergent equals come together. That's a little trick to help you remember. They both start with a C. Now, another thing that should let you know it's convergent is if you look here, it's a subduction zone, which is what it says right there. And a subduction zone is a characteristic that we see only at convergent plate boundaries. So that's another hint that it's convergent. So what is actually happening at the plate? All right, so oops, I'll just leave it like this. All right, so we know that this is oceanic crust, and on this side is continental crust. And we did our lab, our snack tectonics lab, where we had the fruit roll-ups and we had the graham crackers. And when we did this lab, we had the graham crackers representing the continental crust and the fruit roll-ups representing the oceanic crust. So when we started to push those two together, we kind of had to, like, I know, make it kind of work for us, because it didn't totally work. But you put the graham cracker on top of the fruit roll-up, and that is called a subduction zone. And why does that work? Well, it's because that oceanic crust is more dense, and so it subducts or sinks. So subducting equals sinking. And when it does that, there's friction and there's heat, and it melts underneath. And what happens is then it creates a volcano. So you can see here that this magma is being created because this plate is melting. And can't really see that. It's red on red, but and bam, pow, kablam, or whatever. That's our volcano. Okay, so this magma creates the pressure, or the magma and the pressure from that plate being subducted makes a volcano. So the next question is, how does that relate to the ring of fire? Let's do the song a little bit. I don't know if I'm actually going to put a song in here or not, but I should. Okay, so the ring of fire. This is the ring of fire, and it's a place known in the earth, on the earth, to have tons of volcanic activity and tons of earthquake activity. But why is that? Well, if we think back to the questions just a minute ago, it is a subduction zone, because right here, all of this stuff in the ocean is smashing over, the plates are smashing over to these plates on the other side, and they're coming into each other, and they're converging. And at a convergent boundary with oceanic and continental, we get a subduction zone. And at that subduction zone, we get earthquakes and we get volcanoes. So that's what's happening, is it's a convergent plate boundary, and it makes volcanoes and earthquakes. Yes, I know that's spelled wrong. I fixed it. I don't know why it didn't save. So sue me, okay? All right, lay off. Just trying to make a study guide party here. All right, so now we're going to question number 2. Question number 2 is talking about tectonic plate theory, and it says that it's including the idea of convection currents moving the plates. So how do they do this? How do they pull them along? So you remember our song, I'll do it and you can join in with me. Okay, now you better sing along or else it's going to be awkward if I'm doing it by myself. Okay, ready? Convection currents. Less dense rises. More dense sinks. Hotter rises. Colder sinks. And if you want to play that again, you just rewind it, play it a few more times, put a B to it, probably. That would be amazing. We could probably sell this on iTunes. All right, so we know that that's the rotation of matter inside of the mantle. So here's where we have to apply. In class, I said to you guys, some people say, our tests are never what we've learned. And yes, they are. So here's the difference, though. Way back when we didn't have phones, we didn't have internet, you had to know a lot of stuff because it wasn't easy to get access to that information. Well, today, in our world, you can grab your phone out, you can go to a computer and find like anything you want. But the real important skill as a learner is to apply it. So everything that you're going to see is an application of what we've learned. So what I want you to do is to lay this 93 flat, and I told you to do this in class. Whether you listened or not is a different story, but I told you to take your fingers, put them on the paper, find those arrows, and this is your physical challenge. Can you actually follow the arrows with both fingers? All right, now let's look at this first box. You should be making little circles, little circles. It's hypnotizing. Don't fall asleep. And as you're moving them, you'll notice that as your convection current gets up to those little rectangle boxes, which are the plates, they start to move away from each other. So what are those plates going to do? They're going to move away from each other, and that is what kind of plate boundary? Oh no! We're still here. That is a divergent plate boundary. They're moving away from each other. All right, and now go to the next one over and make your little circles. Okay, so we know that our first one over here, as they came up to the plate, they start to go in this direction. So on this other one, you're making little circles. Again, don't fall asleep. Make little circles. Wax on, wax off. Okay, well, let's see. As they're coming up toward there, they're moving in toward each other. So what are those plates going to do? They're going to get pulled in and converge and either make a mountain or a subduction zone or something like that. All right, so now we're going to switch over to question number 4. I think I'm going to move myself over. Okay, so now we're going to look over here on question 4. And I said in class, as a scientific thinker, it's super important to try and be kind of skeptical of the information you hear because we ask questions and we try to find evidence to support the answers. And if somebody's telling you something, you better say, what's your evidence? So let's look over here at our first fact. So for this one, you have to find out, what is the fact? Someone walks up to you and they say, you know what? Tectonic plates used to be together. Because that's a pretty typical kind of, conversation starter. So you say, oh, plates used to be together. What's your evidence? So now let's look at the evidence. In this picture, we have one continent. This is Africa. Oh, no. Let's pause. Okay, so we've got our 2 continents right here. That's Africa. And over here is South America. And you'll notice that they fit together really nicely, like surprisingly so. Like so much so that they had to be together. There's no other rational explanation. And it also ties in not just the shape, but the layers of rock that they have. And if the layers of rock are similarly layered on each side, then the rock had to be there together at the same time. So because these fit like puzzle pieces, they must have been together once. That's our evidence to tell us that, yeah, the plates used to be together. The next piece of evidence, or fact that someone says is, the plates used to be together. And you say, because you're a smart science thinker, you say, well, what's the evidence? So let's look at some different evidence. Over here we have fossils that are very similar. In fact, they're so similar, they're the same. And in this dark green band you see, you've got the area in which those fossils were found. Well, let's look at this. South America and Africa are way far apart right now. So how did those reptile creature things get where they are in the fossils? They couldn't just swim across the ocean. So what do we know? That the plates had to be together because the fossils are on the same pieces of the continent. And we saw before that they fit together nicely, those continents. So here's another layer of evidence, pun intended, that tells us that the continents must have been together. All right, let's look here. Now this is called, paleoclimate data. So it just means like old climate. That's really what that means. So old climate data. Now an ice core, if you want to go pause this and look up what an ice core is, get some pictures in your head of what that is, you can do that now. I'll wait. You're back. Okay, so an ice core is pretty much just a tube. You go in the ice, the glacier, you pull up this huge tube, and it's this big column of ice, and it records sort of lots of information with the gases that were trapped there and the particles that were in the air at the time that got trapped into the ice. And so they can find out similar patterns in the oxygen content, too many continents, the oxygen content, carbon dioxide content, as well as the temperature at the time. So if you pull an ice core at the North Pole, and you go to the South Pole and you pull another one, guess what? They have very similar patterns. So what does that tell you? Well, they had to be at the same place at the same time in order to have this similar climate pattern. So because the weather and climate was the same on places that are far away today, that means they had to be together at some point. All right, let's look here. Earthquakes occur a lot where plates are moving past each other. How do we know that? All right, so on this picture, you can see all these little circles. Well, look, they're kind of making this pattern. Hey, that looks familiar to the Ring of Fire. And remember, we talked about how the Ring of Fire is where all these plates are merging and converging. And so these are plate boundaries. Now, I got this from a live earthquake website. And if you go to chalk up to the blend space for the tectonic links, take some time to check out where the earthquakes are occurring on Earth. And you can select from like today to the past week, to the past month, to the past year, etc. And it's kind of awesome to actually see where the earthquakes are occurring. And you will see that this pattern holds true. So if the earthquakes are happening, you see this line of the trend where everything is located. And that tells you that the earthquakes are indeed happening at the boundaries. They actually, it's like playing connect the dots. You can connect all the dots where the earthquakes are, and it tells you essentially where all the plate boundaries are. All right, another piece of evidence is this GPS data. So someone comes up to you and says, plates are constantly moving on Earth. Well, if you look around, like nothing really looks like it's moving, right? Because you look at the ground, it's pretty steady, thankfully. So you're probably thinking, well, how do I prove this? Because it's moving really slowly. We can't see it. So what we can do, however, is use satellites and kind of that more advanced technology and use GPS data. And so this positioning system of these satellites is able to track specific spots on the planet. And as it does this, we can actually graph or map it out and kind of plot the data of the different velocities. And you can see all these arrows. These are vectors that should ring a bell. And the longer they are, the faster that plate is moving. And so you can see that they're going every direction all over the entire planet. And that gives us evidence that they're moving all the time. All right, last but certainly not least, this one's a little tricky, so just kind of get the gist of it for now. But the plates are moving apart, is what somebody says to you. And you say, how do you know? Well, let's look at this data. So the age. This is age 0. That's fresh, new baby rock. It's so cute. Do you see it? It's so cute. All right, so that's our fresh baby rock. Well, if we look over here, 10 million years old and 10 million years old. That's the oldest rock in this picture. It's getting pushed away. So remember my example. This is seafloor spreading. It's at the bottom of the ocean, and it's at a divergent plate boundary. So you get your cake. You cut your cake, and you push away the sides. You put a new piece of cake in. You cut that, and you push it away. You get a new piece, cut it, push. New piece, cut, push. New piece, cut, push. Whew, you have a really long cake. I don't know why, but you do. So just go with it. And so now, when you look at this cake, where is the newest stuff? It's right in the middle. That's the brand new stuff. And that's the magma that's rising up as the plates move. Then on the end is where that oldest rock is being pushed to the side. And someone in class came up with a really good way to think about this. They said, think about this. The new baby in the family is the center of attention. Oh, so cute. And then the older kids get pushed to the side. So that's a good way to think of it. But not only that, but these are the patterns that are created by magnetic stripes. So what does that mean? Okay, so remember, the Earth has a North Pole and a South Pole. And we use our compasses, and we get really excited that we know North is at the top of the relative top of the planet. And then we say, well, that's really good. That's where North is. Well, guess what? Hundreds of thousands of years later, the poles have switched. The planet doesn't flip, but just where the North and South poles are indicated by magnets is going to flip. And it has been doing this for the entirety of Earth's existence. So what happens is this fresh magma comes up, and just like those iron filings, when we bring a magnet near them, they line up, and they organize and orient themselves to the North and South poles. Well, guess what? The minerals inside of the magma line up and orient themselves to the North and South pole. They solidify because the rock was this liquidy magma, and it's now hardened and turned into solid rock. So now, a few more thousands and thousands of years later, more magma comes up, but guess what? The poles have flipped. So now what happens is the new magma aligns itself to the new North and South, and it solidifies. And the magma pushes away, and all this old rock gets pushed to the side. But it has since recorded where the North and South poles are based on the fact that they have kind of frozen themselves into that position as they've hardened. That's kind of a lot to say, but really just the gist of it is the new rock is in the middle. It pushes out the old rock as the new rock comes up, and as it hardens, it orients itself to where north and south is. Okay, that one's a little complicated. Maybe watch that one again or go and watch that. Well, okay, I'm not going to recommend watching that creepy video because you might have nightmares, but it was pretty good. So you might want to go watch that creepy video again or see if you can find another one about that. It's called paleomagnetic. I'll write that. Magnetic data. Well, it kind of looks like it. Just go with it too. So paleo means old, magnetic means magnetic. Right. All right, so now we are going to look over yonder. And I don't know where to put myself. Let's go here. Okay. Number 5. How is a hot spot volcano like Hawaii different from what happens at a convergent plate boundary? And this was our sci-fi this week. So what happens here? Normally a volcano subducts and is created there at a convergent boundary, or a divergent boundary, pulls apart, and the magma comes up and makes a volcano. But a hotspot is totally different. Hawaii is just like sitting out there chilling in the middle of the Pacific all by itself. Like literally, look at a map. It's crazy how far from everything it is. So where did this magma come from? So hotspot is this place where the magma just rises up, not at a plate boundary. It's kind of just an opening where the mantle has access to the crust. And so it just kind of shoots straight up and keeps piling on more and more magma until you get this island, a volcanic island, and that's what Hawaii is. So why is it in this chain? So in this case, the plate is constantly moving. So as the magma comes up, boop, it makes a mountain, and the plate moves. And now the magma comes up again, and boop, it makes another volcanic island, and the plate moves, and then whoop, way back here, another one. And so what's happening is this plate is moving, and it's extruding this magma to create all these different islands, and that's why we have an island chain in Hawaii. So here's my example from class, and if you feel like going to play the game after this, I'm going to convince you that you should study first, and then you should play the game. But if you play Super Mario Brothers or Mario Kart, silly me, and you play it and you drive around and you drop off those little banana peels, that's like the plate dropping off the volcanoes essentially. So that's a good analogy to help you. Okay, for number 6, you are going to be listing the features or events. I'm going to move myself. Oh, I shouldn't have drawn that. Ignore that part. It never happened. All right, so here you're listing the features and events that you would see at different plate boundaries. This is all page 89, as well as your processing on 90 and 91. If you did not do your processing, you should probably go do that as a way to help you study. All right, these are literally just a list that we had from before. Make sure you understand it. Use hand gestures, draw pictures, etc. Don't forget, a fault at a transform boundary is literally just like a crack between the plates or within the plate that creates that volcanic action, or the earthquake action. And that's it. You guys just look at your notes or the key for that one. Okay. So draw an image to represent what happens at plate boundaries. Again, this is at page 89, and convergent, remember, come together. Divergent means go apart, and transform, is really slide side to side. You may steal my dance moves. You don't even have to tell people where you got it from. Actually, please don't tell them where you got it from. All right, so now, last but not least, number 8 is about, let's put me up here. Boop. Okay, seafloor spreading. It happens at divergent plate boundaries. And I talked about this just a bit ago, so hopefully it doesn't sound too unfamiliar. So we had to label where it's the newest and the youngest. So newest is right in the middle. That's where the fresh baby magma, so cute, is going to come up and make that new rock when it cools off in the water. Then it pushes all that old stuff over, and that's why the oldest stuff is on the outside. And then finally, you had to explain how magnetic reversals, that just means where north and south flip position, how does that indicate that their seafloor is spreading? So the rocks will align to the North Pole on Earth and solidify there. And when the North Pole flips, the new rock solidifies in that position, and it's on the same on each side. So if you look at this picture, they're both facing south, they're both facing north, they're both facing south, they're both facing north. Okay, now obviously this picture is kind of confusing, but they're talking about how the north and south stays the same, but they're saying that the north is where the North Pole is, and then it flips to actually where the south is, and it flips to where the north is. Okay, So you have all the information you need. Definitely go back to your essential learnings and draw some pictures next to it. And even with this study guide, draw some pictures that help you highlight things that you need to review and draw some pictures. Again, pictures are really good and valuable. Or go find a video on YouTube or look at all the different ways that you plan to study for the study, how to study plan, which is on page 95, and take advantage of the extra time this weekend that you have. All right? Happy studying, and thanks for joining me. No, I can't stop it. Ah, you're stuck with me. Wait, no, seriously.